Alright, so from previous video, we discussed something about the second order differential equations. And in this video, we are going to discuss the higher order linear homogeneous differential equations with the constant coefficients. And the general form of that is look like this. The a0, a1, and an, they are all the constants. And the y here is their independent variables and their corresponding primes. An important assumption we make is still y is equal to e to the rx. Like I mentioned in the previous video, it's because the exponential law in the derivatives tells us no matter how many times derivative you take for that, it will always equal to itself. So, for this one, it will be like a multiple of these exponential terms. For example, if it's y prime, it will actually looks like this. It's r times e to the power of r times x, and if it's r to the second prime, it's r squared times the e to the power of r times x. So eventually, the characteristic equation of this differential equation will look like this. Still, use my small tricks from the previous video, which we just drop down the coefficient here, and the number of the derivative you take for the independent variable here is equal to the number of power here in the characteristic equations. And we still have different scenarios for the root of this polynomial. First is we have multiple different real solutions. So the real roots for the characteristic equations. For example, we have R1, R2, and R3 for the characteristic equations. They will actually correspond to the exponential terms in here. And we just add the constant to them, and we eventually add them together to get the solutions. So you got the ideas. Let's take a look at an example. If a differential equation is look like this, if this third order differential equations, because the leading term here, it takes the three derivatives for the y. And the corresponding equation for the characteristic equation is look like this. You still drop down the constant, and then it'll look like this. So in order to solve this, we'll first try to use some common random number. For example, we let r equals to 1. Alright, let's first try to see whether it's equal to 0. So here should be 1 minus 12 plus 11. So this should be 0. So now we know r equals to 1 is a root of these characteristic equations. So we can simplify this to something like r minus 1 times something else is equal to 0. So in order to solve this, we can use the long division method, where we can put the polynomials here and then divide by this. So it's too long to dive too deeper here, so I will leave this as a self-exercise. You can try it by yourself, but the answer for this is r squared minus 5 times r and plus 6. So this is the quadratic equations which we are familiar with, and we can use the cross method to further simplify this. So in this root form, we can clearly see the three roots of these characteristic equations, and they are 1, 2, and 3. And then we just simply write them into the exponential term. E to the x, e to the power 2x, and e to the power 3x. And then we add the constant to them because they are different independent solutions. And we eventually got the solution for this differential equations. All right, and the next case is when we have multiple same real roots. So just like our previous video said about the second order differential equations, when we got the same roots, in order to make them different, or in order to make them become independent, you need to multiply a variable to one of the roots to be differentiated from other roots. For example, if we got r1 equals to r2 equal to r3, they're all equal to a. And their corresponding exponential terms will look like ax, ax, eax. All right, so the way we try to solve this problem is we will multiply a independent variable, just a variable to this. And in order to be differentiated from these two, we might need to multiply the x for the second time, x squared. So then we add the constant to these three terms. We add them together and eventually got the solution. Let's take a look about another example. All right, so now we can see this equations. Again, we first write out the characteristic equation for this. And then, again, we can try some common numbers. For example, r equals to 2. So it's 2 to the third power, 6 times 2 squared, plus 12 times 2 minus 8 equals 0. So this will be like this. And they're cancelled out. So 0 is equal to 0. So r equals to 2 is a root of this characteristic equations. So we can simplify this like something like r minus 2 times something is equal to 0. So again, we can use the long division method in the first case. And the eventual answer for this is r minus 2 to the square. So these terms are same, so we can combine them together to one term. So this tells us we actually have three roots, but they're all the same. They're all equal to 2. So our first step is to write out the exponential form. And in order to make them differentiable, or in order to make them different, we multiply a variable. And then we add a constant. And then we add them together. And this is the solution to this. And if you want, you can factor out the common terms, e to the power 2x, and you can get something like this. All right, so the third situation is when you have the complex roots. And you can imagine there are also two subconditions, if they are same or if they are different. So let's talk about if they are different. So if they are different, let's take a look at about an example. So actually, it's pretty similar to the second case, which I just mentioned. If you got something same, you probably need to multiply a variable to one of the roots in order to differentiate with another, in order to make it different from another root. because we requires to have like independent solutions for the differential equations. So for this, we will first write out the characteristic equations. So it will look like this. And to solve this, I will use the u. I will set a u as equal to r squared. So then we can turn this into a quadratic equation. And this is what we familiar with. Use the cross method. We can further simplify this into the root form. So we can know u1 is equal to -1, u2 is equal to -4. And don't forget, it's actually r squared. So r squared is equal to -1. That tells us the r1 is equal to plus n minus I. And r2 is also equal to the -4. So the r2 is equal to plus n minus 2I. So from this, we can use our formula, which I mentioned earlier in the previous video, is actually equals to since r is equal to some complex number, and we just put the a and b into their corresponding part. And at here, a is equal to 0, and b is equal to 1. So for this, it's similar. We can write a solution for this like this. And eventually, if we, alright, let's recall for the complex solutions formula. If we got a complex number, the solution will look like this. And we just put a and b into their corresponding part. So yeah, I put here if someone feel confused about this. So our eventual solution for the differential equations will just by adding these two solutions together. So it will look like this, because we have e to the power 0 is equal to 1. So we can just have the solution look like this. And the last scenario is we have different complex complex roots. So pretty similar to the first case which we mentioned. If they are different, you don't need to multiply the variable in front of the solutions. You just add them together. So let's directly take a look about the example. If we got some differential equation like this, and again, we will first write out the characteristic equations like this. And to solve this, we will let u equal to r squared, so that we can simplify this to a quadratic equations. And if we take close to the look at this, we can simplify it like u plus 1 squared equal to 0. And from this, we know that there are two roots, and they're same, they're equal to -1. And since we assume equal to r squared, so r squared is equal to -1. This tells us r1 equals to r2 equals to plus n minus I. And then we can write out the solution based on this formula. So it's equal to C1 cosine x plus C2 sine x. But notice we have two same roots. So we can imagine we have some roots look like this. They are same. But in order to make them different, we need to multiply an independent variable x here. And then we can safely add them together to get our eventual solution for this differential equations. Alright, that's our eventual solution to this differential equations with the characteristic equation that has two same complex roots. Alright, so finally, let's summarize what we discussed so far. So we discussed how to solve the higher order linear homogeneous differential equation with a constant coefficient. And our tools here is still the characteristic equations. So our first step is always find the characteristic equations. And the second step is find the roots of it. And we know there are three scenarios where you have two different real roots, and you have should be multiple, where you have multiple different real roots, or you have multiple same real roots, or you have multiple complex roots. And for the complex, you still have the same and different case, but they apply the same principle as the first and the second case. So let's dive deeper to this. When you have multiple different real solutions, say R1 equals to A, R2 equals to B, and R3 equals to C, you can just simply convert them into the exponentials and add them together. And you will get the eventual solution on this. And when you have multiple same solutions, multiple same roots, say R1 equals to R2 equals to R3 equals to A, same, you just convert that into the exponential first, and then multiply the independence variable, just variables, and then multiply the constant, add them together. You will get the eventual solution for this. Third case is when you have complex roots, and if they're if they're different, say you have R1 equals to A plus minus BI, R2 equals to C plus minus DI, the eventual solution will just by adding them together. And if they're same, say R1 equals to R2 equals to A minus BI, you just need to multiply a variable to one of the roots to make it be different from another. So it will be look like this. Alright, the important thing to remember here is the number of the differential the order of the differential equations is equal to the number for the roots. Of the characteristic equations. Is equal to the number of the constant you should have. Alright, that's all for this video. And if you like it or you have any questions, feel free to leave the comments and please give me the kudos. And thanks for your listening.